The 1969 laser reflector experiment confirmed an astonishing truth. The Moon is steadily drifting away from Earth. Though moving at a seemingly insignificant rate of 1.5 inches, about 3.8 centimeters, per year, this retreat has dramatic long-term consequences. Scientists in the 1990s turned to powerful supercomputers to simulate what happened during the colossal impact that gave birth to the Moon. What they found reshaped our understanding of Earth's early dynamics. Their models revealed that the collision between Theia and Earth wasn't a head-on crash, but rather a glancing blow. This tangential impact imparted tremendous angular momentum to Earth, sending it spinning on its axis far faster than it does today. In the chaotic aftermath of the impact, Earth rotated once every 6 hours, 4 times faster than its current 24-hour day. Meanwhile, the newly formed Moon, still glowing red-hot from the trauma of its birth, orbited the Earth once every 20 days. At this stage, the Moon was 15 times closer to Earth than it is now, and its gravitational pull was immense. In fact, the gravitational tug of the early Moon on our planet was so intense that it deformed the Earth's surface. A massive tidal bulge, an actual uplift of rock and water, followed the Moon in its orbit, slightly offset due to Earth's faster spin. This bulge created a continuous drag on Earth's rotation, while simultaneously tugging the Moon forward in its orbit. This interplay of forces led to a phenomenon known as tidal acceleration. As the Moon's gravity pulled on Earth's bulge, it gained orbital energy and slowly spiraled away. Simultaneously, Earth's own rotation slowed. Over time, the day lengthened from 6 hours to the 24 hours we experience today. And while this change took hundreds of millions of years, its effects were pivotal to shaping a stable, habitable planet. The Moon's close proximity, however, came with a cost. It found itself in the firing line of a brutal, celestial bombardment. Approximately 4 billion years ago, during a period known as the Late Heavy Bombardment, or the Lunar Cataclysm, a gravitational disturbance between Jupiter and Saturn altered the orbits of countless asteroids in the outer solar system. Many were flung toward the inner planets, including Earth and its newly formed satellite. The Moon, then only about 86,000 miles away from Earth, bore the brunt of this onslaught. Thousands upon thousands of meteorites pounded its surface, destroying approximately 80% of its crust. Immense craters formed, some stretching hundreds of miles across. Molten rock erupted from fissures caused by impacts, flooding craters and cooling into vast basalt plains, which we now call Maria, Latin for seas. One such sea, the Sea of Tranquility, would become the landing site for Apollo 11 nearly 4 billion years later. From Earth's surface today, the pattern of these dark basalt plains creates the illusion of a face, the famous man in the moon. But those features are scars from a savage past, a violent record of the solar system's chaotic youth. Astrophysicists like David Kring have studied these craters in extraordinary detail. Some number over 300,000, ranging in size from half a mile to more than 500 miles in diameter. The largest visible from Earth is the Imbrium Basin, which stretches nearly 700 miles across. These impact sites are far more than cosmic curiosities. They're time capsules from a forgotten age. Occasionally, the impacts were so powerful that debris ejected from the Moon's surface didn't fall back. It was hurled into space. Some of this lunar material was drawn into Earth's gravity well and fell to our planet as lunar meteorites. Only about 30 such meteorites have ever been found, but they are invaluable. Embedded within them is a geological record billions of years old, far older than any rock found on Earth, where erosion and plate tectonics have erased nearly all traces of our earliest history. The discovery of these meteorites sparked an intriguing question. If rocks from the Moon could land on Earth, could the reverse be true? Could early Earth rocks, blasted into space during the cataclysm, have landed on the Moon? And more tantalizingly, could those rocks contain chemical signatures of early life? Launching anything from Earth into space requires immense energy. NASA's space shuttle, for instance, used over 15 million horsepower to break free of Earth's gravity. By comparison, the lunar module needed just 6,300 horsepower to escape the Moon's weaker gravity. The difference is immense. But during the lunar cataclysm, Earth's surface was pounded by meteorites and asteroids of extraordinary size, some even larger than the impactor that wiped out the dinosaurs. These impacts punched holes in Earth's atmosphere, allowing fragments of Earth's crust to escape into space. Some of that material, by sheer gravitational alignment, could have landed on the Moon, preserving early traces of life in the vacuum of space, protected from erosion, weather, and geological recycling. Astrobiologist Guillermo Gonzalez estimates that over 1,000 pounds of terrestrial rock could be spread over every square mile of the Moon's surface. If even a few of those rocks contain organic molecules or fossilized microbial life, they could help answer one of humanity's oldest questions. How did life begin on Earth? So far, no confirmed Earth rocks have been identified on the Moon, but future lunar missions may one day uncover these time-traveling messengers, offering a glimpse into the ancient story of our planet. In a strange twist of fate, the Moon, a lifeless world, may hold the most pristine record of Earth's origin story.